The answer to the first question is really pretty obvious. 10 energy units is not going to be sufficient to supply 4 energy units to kinetic energy and an additional 8 units to potential energy. You just don't have enough energy. You need 12 units to supply 8 to potential energy and 4 to kinetic energy. Okay, so second question. We have 2 mass units going from rest to 3 velocity units. Okay, so to go from rest up to 3 velocity units, according to the rule given, which is that the number of energy units is going to be half the product of the number of mass units and the square of the number of velocity units. It's going to be 1/2 times 2 times 3 squared. Okay, the 1/2, the 2 mass units, the 3 squared energy units. Now, we could write that. I wrote this without units because the way the rule is given, that would actually be permissible. But if we want to do it a little more rigorously, we would write 1/2 times 2 mass units times the square of 3 velocity units, which gives 9 mass units times velocity units squared. And that would give us then 9 energy units. Doesn't matter what the mass units are, doesn't matter what the velocity units are, doesn't matter what the energy, well, yeah, it does matter. It doesn't matter what the mass units are. It does matter what units we use for time. So the velocity units will follow from the units of distance and the units of time. As long as we have set units, we get valid results. Now, these results might or might not easily lead to useful conclusions. We need a good system of units in order to make the analysis as simple as possible. But all this is completely valid. Okay. Next question, we have 2 mass units from rest to 5 velocity units. And by calculation very similar to this one, that's going to require 25 energy units. We take half of the 2 mass units and the square of the 5 velocity units. Calculation would look just like this, except we'd have 5 here. And we would end up with 25 here. So, we also are lowering 2 mass units by 2 distance units. Now, the rule says if we raise a mass unit by a distance unit, requires 10 energy units. If we lower a mass, then each mass unit through each distance unit will provide us with, again, 10 energy units. So if we lower 2 mass units by 2 distance units, well, each mass unit in each distance unit gives us 10 energy units. So 1 mass unit lowered 2 distance units would give us 20 energy units. And then if we have twice that many 2 mass units, 2 distance units, going to give us 40 energy units. So, including the 10 energy units that were said to get from work, we get 40 additional energy units from the fact that the mass goes lower, giving us 50 energy units available, and only 25 of those are required to speed up. So if we don't have something else dissipating a lot of energy or somehow requiring a lot of energy, yes, we can certainly get the 25 energy units that we need from the 10 energy units from work and the 40 energy units from lowering the object, from decreasing its potential energy, if you wish. Okay? Then, our answer, of course, is, we move on to number 4. The quantities are the same as before, except that we're going to require an additional 7 units of energy to do the work against friction, to overcome friction. So, we still have our 10 energy units from work on the object. We still have 40 energy units from lowering the object, and that's a total of 50 energy units. And we need only 25 of those to accelerate our mass, our 2 mass units to a velocity equal to 5 velocity units. So we still have plenty left to do the 7 units of work against friction. The 50 units are available, and we're going to still be left with 18 units of energy. And hopefully we don't have something else in the system that requires those 18 units. So this is just like a bank account, just like accounting. Okay, you have so much energy, you can put energy in, you can take energy out. The energy can go into overcoming friction, the energy can come into speeding objects up, the energy can go into increases of potential energy, and of course a decrease of potential energy puts energy into the bank. Next question asks for how many velocity units we can get from rest from 100,000 energy units applied to 40 mass units. Okay, well, we know from what we have here that if we take half the number of mass units and multiply that by the square of the number of velocity units, we get the number of energy units. And that can kind of be summarized by 1/2 mv squared equals kinetic energy, because kinetic energy is energy of motion, and this is how we calculate it. Now, if this is the case, then we can easily solve for V, and we get twice the square root of kinetic energy divided by m. So if we have 100,000 energy units available, how fast can we get this 40 mass units going from rest? Well, it's going to be the square root of 2 times the number of energy units divided by the number of mass units. If you get the energy units by multiplying the number of mass units times the squared number of velocity units times 1/2, it follows immediately that that the number of velocity units you would have for number of energy units and a given number of mass units will be this expression. And you can work that out, but here it is symbolized in a way that makes it a little easier to see. Okay, well, anyhow, so we do this. We do 2 times the number of energy units, which is 1,000, divided by the number of mass units, which is 40, and we do all that, and I believe we get 71 velocity units. Now, there are 3 systems of units in somewhat widespread use. One is the CGS system, where your distance units are centimeters, mass units are grams, and time unit is seconds. There's the SI, where the distance unit is meters and the mass unit is kilograms. Time unit again is seconds. And the time unit is again seconds in the old British system, which is still widely used in engineering, probably more so in the United States now than in Britain. And that's where your distance unit is in feet, your mass unit is the slug, and again, your time unit is the second. So the only thing here that really depends a lot on the system of units is how much energy it takes to raise or lower to raise an object against gravity, and how much energy you get when the object is lowered in the direction of the gravitational force. Okay, so that 10 unit conversion is pretty consistent with the SI system. But there's a 1,000 unit conversion that we're going to see shortly that would go with the CGS system. 1 unit of altitude in the CGS system corresponds to, 1,000 units of energy, not to 10. And in the British system, it would be 32. Okay, so again, the system determines that one quantity. This, well, I don't have it written down coherently here, but you've seen it on your sheet, on the problem set. Okay, so that's just a little prelude. Everything we're saying here is not system dependent, except that 10 energy units for one mass unit raised, one distance unit.